Hello there, this is the second video about giant structures, and in this one I'm going to look at giant covalent structures. So I'm going to start off looking at graphite and diamond, and they're two different solid forms of the element carbon. After that I'll have a look at silicon dioxide. So graphite and diamond are both solid forms of the element carbon. As you can see from the diagrams, their atoms, which are all of carbon, are linked in different ways. And that gives the two very different properties. So they're called allotropes, and they are different forms of carbon. So let's start off having a look at graphite. Firstly, we need to appreciate what the solid lines represent and what the broken lines represent. Okay? The solid lines are covalent bonds, and the broken lines are weak forces of attraction. So let's have a think about the structure. If we pick this carbon atom here, you can see that it forms 3 covalent bonds. Now it's worth bearing in mind this diagram shows a tiny bit of the structure of graphite. If you looked at an entire sheet, every carbon atom would form 3 covalent bonds. Now carbon's in group 4 of the periodic table. That means each atom of carbon's got 4 electrons in its outer shell, only 3 of which are involved in bonding. Therefore, the 4th electron becomes delocalised and it can move throughout the structure. And that is why carbon in the form of graphite conducts electricity. Now also in graphite we've got layers with weak forces of attraction between the layers. The layers can slide over one another, and that makes graphite extremely soft. Graphite is a substance that they use in pencils, so when you're rubbing a pencil on a piece of paper, the layers can slide over one another, and that allows the pencil to leave a mark. So other uses of graphite include in batteries, in lubricants, and when you do electrolysis, the electrodes are probably made out of graphite because it's a good conductor of electricity and it's fairly unreactive. Now if we have a look at carbon in the form of diamond, things are very different. So if we start off by picking this carbon atom down here, we can see that that carbon makes 4 covalent bonds. And if you looked at a much larger diagram of a structure of diamond, you'd see that every single carbon atom made 4 covalent bonds. Now, for that reason, all the outer shell electrons in carbon are involved in bonding. There are no delocalised electrons, so therefore carbon in the form of diamond doesn't conduct electricity. Now notice that there are no layers in diamond. It's got a tetrahedral lattice, and that makes diamond exceptionally hard. So uses of diamond would include jewellery, cutting tools. It's often on the tips in drill bits and engraving tools. Now both diamond and graphite have got extremely high melting points because all the covalent bonds need to be broken in order for either of those to melt. For graphite, it's not enough to simply overcome the weak forces between the layers. Now finally, if we have a look at silicon dioxide, which is the main constituent of sand. Now its formula is slightly misleading as SiO2 because that makes us think that we might have a molecule with 1 silicon atom and 2 oxygen atoms. In fact, that shows us the simplest ratio, 1:2, of atoms of silicon to oxygen actually within the structure. So if we look here, these bigger atoms in the middle are silicon, and silicon, like carbon, can form 4 bonds, and the ratio of silicons to oxygens is 1:2. Now let's think about this. If we contrast this with diamond, silicon's got 4 electrons in its outer shell, and they're all taken up in bonding. Therefore silicon dioxide doesn't conduct electricity. Silicon dioxide, for the same reasons as diamond, is also very hard. Think about it, it's used in abrasives like sandpaper. Also, silicon dioxide's got very high melting and boiling points because you've got to put an awful lot of heat energy in to break all those really strong covalent bonds. Okay, thanks for watching. So hopefully that's giant covalent structures made simple.